Again, welcome to our webinar series. Our latest for this series, WaterTAP modeling. And we've got the WaterTAP team here with us, and they have got a great program for us. Some housekeeping to begin with. We record these meetings so you and your colleagues can review and go back, and they are available on NAWI's YouTube channel. We will keep you muted during the event, but we recommend that as questions come to you, pose those questions in the chat right then and there. And then at the end, I will come on and hopefully unmute you, and then we can have you ask your questions directly of our speakers. Follow us on LinkedIn. This is how we are communicating with our more than 4,000 people in the NAWI sort of listserv. Seriously, just go use the scan block and you can follow us on LinkedIn if you are not already. One clue, whether you are following us and signed up, are you getting NAWI's dispatch? If you're getting emails monthly called the NAWI dispatch, then you are signed up. Also, if you're curious about our growing library of past webinars, you can always check out our YouTube channel here and just zap that QR code and you can learn more. Next month, on August 19th, we will have a special session, not one, not two, but three different pilot teams. Team 317, 319, 320 will all come on and talk about the pilots that they have been executing and in many cases just winding up. They'll give practical advice and share some of the key tips that they've learned, not the sort of stuff that goes into publications, the serious stuff that makes science work or not work. This is particularly highly relevant because NAWI is about to release its latest funding opportunity in industrial water reuse pilots. And so for any of you out there contemplating putting together a proposal, getting some of this practical advice about partners and facilities could really help. All right, we always have to do our disclaimer, and you can read it yourself. I'm not going to go through that. But I just want to start and introduce NAWI and the WaterTAP team this way. Many of you were not aware of this, but 10 years ago, the DOE published a report and actually designed a report to first assess whether desalination had kind of room for improvement. This work was done largely at Lawrence Berkeley National Laboratory by Prakash Rao, and in it, they sort of tried to unpack ocean desalination and figure out where the key opportunities were for squeezing out additional energy and cost savings. Now, interestingly, at the time, the analysis in the frame was entirely sort of technological, better membranes, better pumps, et cetera, cheaper alloys. And the whole subject of process optimization was just very, very oblique. And what's really interesting to me is that this has turned out to be one of the key places where the NAWI program has delivered a huge benefit to the water community in general, and that is with WaterTAP. So what is WaterTAP? By the way, you can scan it here and it goes directly to NAWI's website with the WaterTAP information. For water treatment system designers, water treatment technology developers, and water treatment researchers, WaterTAP is an open source software modeling system that can accurately estimate the physical, chemical, and economic performance of water treatment systems. Unlike custom-built or industry-provided unit process models, WaterTAP can ensure users to perform closed-loop optimization of prospective treatment trains and can quantify the individual performance contributions of specific unit processes and improvements to those unit processes. That is what WaterTAP is. That is what we're going to learn about today. And I'll just sort of wrap up by saying we've been here before. Way back in the late 70s, a group at MIT realized that process design in chemical manufacturing and oil and gas refining was really still relying literally on slide rules and pieces of paper. And they realized that the early use of computers could greatly advance how we do process design. And so they built Aspen, this system, which then got commercialized and is now used widely across the oil and gas sector and across all of chemical process and chemical engineering. Now, what we realized early in the NAWI program is if we wanted to do the sort of advanced process simulation, we needed a tool like Aspen. And unfortunately, Aspen didn't have a lot of unit processes relevant to water treatment. So that is the origin of WaterTAP. And just as Aspen is a foundational tool in process engineering today, we believe that WaterTAP is going to be a foundational tool used by water treatment engineers, designers, and researchers. And this is what really excites me about introducing Almira Shamlo, Adam Mattia, and where's Kirby? There you are, Kirby. Hello, Kirby. And they're going to talk to you about where we are right now in this exciting program. So, guys, thank you very much for all your work, and we are so looking forward to hearing more about WaterTAP today.
Thank you, Peter. Can everyone see my screen?
Yes, we can.
Great. All right. Hi, everybody. Some of you know me already, but I'm Adam Mattia. I'm currently the lead of WaterTAP. I'm joined here today by Kirby Sitterly, who works closely with us on the team, as well as Elmira Shamlu. The title of today's talk is WaterTAP Modeling for Accurate, Quantitative, and Insightful Technoeconomic Analysis of Advanced Water Treatment Systems. It's a mouthful. So let's start with just a tiny bit more background on WaterTAP for those of you who haven't heard of it. I think most of you have. So WaterTAP is an open source tool really meant for evaluating existing commercial technologies as well as emerging technologies. The idea is that we could take unit models, plug them together into a flow sheet in whichever way we like, use WaterTAP to evaluate that flow sheet, and produce results like this on the right? So we look at the cost optimal levelized cost of water, for example, as a function of water recovery. And we could look at the cost breakdown and compare that system to other systems, right? Everything is publicly available on GitHub, so you could feel free to check that out. We also have extensive documentation. Over the years, we started off with a very simple RO model. We quickly moved on to adding more complexity to that RO model, followed by osmotically assisted RO, nanofiltration, membrane distillation. We have models for mechanical vapor compression, MED, crystallizers, electrochemical models, so electrodialysis, electrolyzers, electrocoagulation, chemical reactors, ion exchange, granular activated carbon, solvent extraction. We have even biological models, activated sludge reactors, anaerobic digestion. And we also leverage some of the unit models from IDEAS, which is another DOE-funded project that we build on top of, which offers up its library to us. So we pull pump models, heat exchangers, mixers, splitters from that library as well. So we have a diverse array of unit models to work with. And what can we do with that? So our bread and butter is really simulation and optimization of treatment trains. Again, taking this modular model library, piecing together unit models, whichever way we like, to evaluate treatment trains, right? And so the idea is that WaterTAP could be a one-stop shop for pre-screening, evaluating these technologies, and ultimately arriving at the lowest cost solution, right, for your given application. Other capabilities that are built in within WaterTAP that can be leveraged: parametric and stochastic sensitivity analyses. So how do my results change as a result of uncertainty, right? Let's say my electricity cost is varying. How does that affect my levelized cost of water? What if membrane costs shift? How does that affect my optimal solution for my design and the associated cost of water, right? So we could evaluate that with built-in tools. Another thing we could do is we could work with collaborators who may have experimental data. Maybe there's simulated data from external tools. We could use that to parameterize our existing mechanistic models, essentially calibrating our models so that we could increase the accuracy and minimize predictive error of those models, right? So again, another thing that's built in under the hood of WaterTAP. And one last thing that I'll mention that's built under the hood is surrogate modeling capabilities. So we could leverage data to either make hybrid models that pull together mechanistic with data-driven components, or we could have an entirely data-driven model where we leverage built-in machine learning tools to fit equation-oriented relationships to those data, okay? And we could plug that into our process flow sheet to evaluate any system we like. Now, another thing, this is more of the cutting edge right now of WaterTAP, is that we've incorporated detailed water chemistry into WaterTAP. So let's take this process flow sheet as an example here. It's just an RO train with softening and recarbonation as pretreatment. What if I want to answer the question of, What are the optimal doses I should have for softening and recarbonation? At what point, at what recovery rate am I going to scale my membranes given the feed composition I'm working with, right? And so these are the types of questions we can answer with this capability. We could predict mineral scaling in our treatment process. We could just as well predict solids recovery if we like, right? And how do we do this? There are two main approaches. You start with your favorite external chemistry simulator, be it OLI, Freak-Z, what have you. We run a bunch of simulations, produce data from that tool. We use, once again, our built-in machine learning tools that we have available to develop surrogate models that we could plug into our process flow sheet model in WaterTAP, okay? That's one way that we could do this. Another way is a bit more direct, where we could directly embed water chemistry calculations in our process flow sheet. And so you could choose either approach. What you'll see later today from Elmira is one example of where we apply this with an industry case study, which is pretty interesting. I just want to point out, using some of the existing free tools out there from, let's say, some membrane manufacturers, you could plug in your specs for your, let's say, your RO treatment train. You could plug in your feed water composition, and you'll get back what the supersaturation ratio may be, the saturation indices with respect to certain mineral scalants, right? So it's sort of a post-process result. This approach answers the question differently, right? We're asking, at what maximum recovery can I achieve to prevent scaling in my system, right? So we're not just punching in specs and seeing what the saturation index will be. We're saying, hey, I need to design my system for the lowest cost without scaling, and the model will produce that result for you if you set it up correctly. Okay. Now, let's shift gears a little bit and dive into our latest objectives for WaterTAP under NAWI 2.0. I just want to make this clear. We started off as an advanced research tool for advanced researchers. We want to broaden the spectrum a bit and let everyone get their hands on WaterTAP, not just advanced researchers who know how to code. And so first and foremost, we want to provide value and solve challenging problems for people with real world systems, pilot projects, industry stakeholders, okay? The other thing we want to do, like I just said, is we want to facilitate broader adoption. One way we're doing this is through what we call the WaterTAP Academy. I see we have quite a few people on today that were part of the first cohort of the WaterTAP Academy. Thanks for joining. Hi. The other thing I want to mention is this call to action. All right, we want to hear from you. We want you to reach out. As Peter mentioned, we're expecting any day now from NAWI to hear about this new NOFO for industrial reuse, right? And so the WaterTAP team will be here to provide technical support for future awardees of that effort. And so we encourage you to reach out to us, engage in discussion. Let's talk. Okay.
Yeah. And
We are
Adam,
here. Yes.
I want to double click on that and say, even beyond NAWI, we know that the DOE has just dropped on the street a very interesting funding opportunity that includes funding for pilots of produced water treatment. There too, WaterTAP is potentially an invaluable tool for you to do the technoeconomic assessment, and that's actually required as part of that funding application. So TEA is here to stay.
Thanks, Peter. Okay. Now, let's just touch on the WaterTAP Academy a little bit for those of you who don't know about it. So we put out a call for applications, I'd say last June, 2025. We received over 100 applications from practitioners in industry as well as academia, and people were excited about learning WaterTAP. So what was the course? It was an 8-week course where we wanted to teach non-developers how to use the tool, right? And here's just a snapshot of some of the different entities that were represented by the people who applied. Okay. Ultimately, we had to trim things down to a very small group. So if you didn't get pulled into the first cohort, don't worry, we're going to have others. And it wasn't you, it was us. We wanted to make sure we could manage our first cohort efficiently. And so we kept the group size small. So we had overall 25 Academy participants, 15 were direct participants of the cohort. The other 10 were part of our project support group that basically gives us guidance on where we should go next with WaterTAP. All right, and so across this group, We had representation of over 15 organizations and at least 13 capstone projects that were proposed by people in the group, which I'll get to in just a second. So just to give you an idea of what the course looked like, again, we wanted to teach non-developers how to use WaterTAP. We wanted to stick through with a central example, just in case people got lost, they could always go back to this typical reverse osmosis flow sheet throughout the course. And by the end of each week, we wanted to be able to achieve certain goals. So the first week, of course, was easy. Let's just set up WaterTAP, make sure you have it running on your system. Week 2, we navigated the code repositories and tried to let people learn about the basic building blocks of WaterTAP. Week 3, we show people how to set up and simulate optimized process flow sheets. And by week 4, we got a little crazy and we tried to show people how to make their own unit models, their own property models, and plug them into flow sheets. All right. So the first 4 weeks is really about building a foundation in WaterTAP. And then weeks 5 through 8 are more about advanced capabilities. So running sensitivity analysis tools, parameter estimation for model calibration. Then week 7, we focus on surrogate modeling using data. So we use some example RO plant data to show how to calibrate your RO model. We also pulled multi-speed pump curves from data sheets and showed people how to essentially bring those into your WaterTAP model. Earlier in the course, we had questions about that. So we thought we'd spice things up and drop that in there. And then by week 8, we finished off with showing people how to incorporate detailed chemistry into process flow sheets with a simple example. By the end of the course, we originally wanted people to be capable of adding their own models and refinements to WaterTAP. But I think after this experience, it's clear that our first goal should really just be to get people to use the tool rather than have them become contributors right away. Okay. The other thing that we did in the course was to encourage people to think about a capstone project. What is this? This is just pick an initial analysis that you're interested in that's relevant to a real project that you're working on, right? And so for week 2, we asked people to brainstorm ideas on that analysis. We asked them to consult with us to get feedback on whether that would be viable within the timeline. We sent that feedback to them, and then weeks 5 through 8 is when they would work on that analysis. By the end of the course, we didn't tell people you had to be done with the analysis. It was pretty loosey-goosey. We just wanted people to apply what they were learning to real projects of interest. And I'll say that after the course ended, we encouraged people to reach out to us to continue working on their analyses. And just to give you a flavor of what people proposed, here's a laundry list of some of the ideas that people had and some of the things that people were pursuing. So everything from pulp and paper applications to copper recovery, evaluating LSR-RO designs. Let's see, I'll pick one more. Screening USBR projects with a new costing package. So we've actually been meeting with USBR quite a bit, trying to see how we could work together using WaterTAP and leveraging it for USBR projects in the future. Still under discussion, but one cool development out of this academy. We can see here from one of our final surveys that there's high interest in people that people have in collaborating with the team after the academy. So people are interested in pilot partnerships, low support analysis, where they do most of the legwork, versus high support analysis, where we do most of the legwork. It could go either way. So if you are looking to get some sort of analysis set up in WaterTAP, reach out and we could point you in the right direction. I'll finish off this section with testimonials. Up until now, it was mostly people from the WaterTAP team praising WaterTAP, like, oh, it's so powerful, but we develop it, we use it. How about people outside of our direct team? Well, this gave us an opportunity to get some validation. So here's testimonial number 1. WaterTAP is the most powerful and flexible program out there. WaterTAP is very useful for screening and optimizing systems across a range of parameters. This capability is nearly impossible to replicate in Excel. All right. Another one, WaterTAP should be shared and used more widely. It's such a powerful tool. And then last but not least, it was inspiring how many talented programmers you have that also have a thorough knowledge of water treatment processes. So this isn't just to toot our own horn. Like on that last point, I just want to highlight that our team comprises experts in mathematical optimization, process systems engineering, software development, but also subject matter experts in desalination, water reuse, water treatment in general. And so I really encourage you to touch base with us. Now I'll shift over to some example pilot support that we've done recently, starting with this NAWI 311 project, which is really headed by Zahi Kath and Jason Rosenblum. Basically, we wanted to use WaterTAP to help with the optimal design and operation of a new low salt rejection RO pilot. Okay, I'll assume that most people are familiar with low salt rejection RO, but just briefly, on the left here, you see the standard LSR RO configuration where you bring the high salinity feed in through the first stage. Your first stage would typically have some seawater membrane elements, followed by low salt rejection stages that comprise high salt passage membranes, right? So essentially you have saline permeate streams that get recycled back to the previous stage inlet, right? So I think most people know what this is. So Zahi and, and James were proposing an alternative configuration. They were focusing on produced water, so higher feed salinity. And they said, well, you know what? It makes more sense to bring a high salinity feed in through the second stage where you have your first low salt rejection train, rather than stress the seawater RO elements by feeding into the first stage, right? And Zahi was, he suspected that you'd have lower energy consumption overall, and maybe even lower cost, but there wasn't anything definitively quantified. So we said, all right, let's look at that. Let's take a look with WaterTAP. But before that, I want to point out that they have a new LSR RO pilot under construction. One of the questions they wanted to answer was like, how can we maximize recovery if we vary feed concentration, right? If we throw this system out in a field, there's going to be variable feed water quality, right? How do I maximize recovery as feed salinity shifts with a fixed system design? Let's say I'm operating my pump at capacity, 45 gallons per minute. Problem is, I have maximum feed flow limitations on my membrane elements. I don't want to telescope my membranes, so I need to stay within those limits. So what we did in WaterTAP to start was to say, all right, subject to those constraints, I do not want to exceed the max feed flow limitations of my membrane elements. Don't want to damage them. So let's add those constraints into the model. And let's set up the model to maximize recovery, this black dashed line here, as a function of feed concentration shown on the x-axis. On the secondary y-axis, you have recovery rate. And now on the primary y-axis, you have feed flow rate. So you can see how this guides the operator on what the feed flow rates would need to be as a function of feed concentration and max recovery for every train, right? And so here's an example of some of the technical insights, pretty simple example, but something that answered a question that the team had that was useful. But then we wanted to go a step further and go back to that question of whether how much could you save in energy consumption, right? How much cost reduction might you see? Let's find out. So with the standard configuration, if we just take an arbitrary example representative of produced water, right? 110 grams per liter TDS feed, 30% recovery. Here's the WaterTAP result showing a cost breakdown for the standard configuration. So we see an LCOW of $3.17 per cubic meter, SEC of roughly 20 kilowatt hours per cubic meter, right? You can see the breakdown here. This is customizable. This is just what I prefer to break it down as. Now let's look at the alternative configuration, right? Where you bring the feed in through the second stage. You could see that LCOW will decrease by 19% and SEC decreases by 14% roughly, okay? So this was reaffirming, but then we asked, well, this is just one point on the map. This doesn't tell you when to use which, maybe there are conditions where the standard configuration will be superior, So how can we evaluate that? Well, we can evaluate that in WaterTAP as well. We could use sensitivity analyses that I pointed to earlier and do a sensitivity on feed concentration as a function of water recovery. And what you can see here on the left in the blue region, this is where the standard configuration is the lowest cost solution. Past this black boundary line in the orange region is where the alternative configuration is the lowest cost solution. So you could see that Zahi's guess was in the right ballpark. He was right. At higher feed concentrations, the alternative configuration relative to the standard will be a lower cost solution. Okay. On the right, what you could see is LCOW savings. So the percent savings versus the higher cost solution. So here on the left of the black boundary, you could see, let's say on this 15% contour line, this says that the standard configuration will be 15% cheaper than the alternative configuration. And vice versa, if I go to the other side of this black boundary line and I pick the, let's say this 20% contour, this says that the alternative configuration would be 20% cheaper than the standard, okay? Hopefully that makes sense. And we could do the same thing if some people just want to look at energy consumption. We could do the same thing with SEC. You could see a similar trend where the standard configuration results in the lowest specific energy consumption versus the alternative. And the trend is that the alternative outperforms at higher feed salinities. So it is likely more suitable for produced water treatment, okay? Now, let's shift gears and talk about some other areas that WaterTAP is looking at. So we're looking at digital twins, right? Currently, for the most part, we lack interaction between our digital models and physical systems. Sometimes we have collaborators send us data to do calibration and inform our modeling, similar to what we did with Zahi and James. But we want to move towards two-way digital twins in the long run, right? So autonomous data exchange between digital model and physical system. Our first lowest hanging fruit to do that happened to be with Diego Rosso at UC Irvine, okay, through Project 509. So essentially, they had a pilot installed at OCWD. It was meant to be representative of the full-scale system. So they called it the physical twin. And then they put together a model using Sumo to represent that physical twin. The idea was that they could do real-time model updating, model predictive control of the physical twin, and automated experiments. Right? Now, if we look at all the steps, you start with continuous data ingestion from the physical twin, followed by model calibration, after doing some pre-processing of the data. Then model optimization. What were they optimizing? They wanted to look at reducing energy costs. So if I have a variable electricity price signal, how should I adjust operation of my system in response to that electricity price signal to reduce energy costs for my system? Okay. So model optimization followed by model predictive control of the physical twin. So whatever the optimization results showed, you'd use those results to change the next set point of the physical twin over the next hour. Okay. This was done on an hourly resolution. Now, we looked at this workflow and we said, whoa, you guys are using Python to do half of this. For the model, you're using Sumo, which is great, but why don't we also try swapping out Sumo for a second and putting in WaterTAP? WaterTAP is built on Python as well. So this seems like a seamless connection. Why don't we try it? So we did. Initially, we had to build a simple flow sheet representative of the physical twin in WaterTAP. So we did that. The other thing is we predominantly have worked with steady state models in WaterTAP. We've hesitated to take the leap towards dynamic or transient modeling. So we took that leap and we created this multi-period model. On the top, you can see the electricity cost with the gray bars. The red shows the energy cost on the system. In the middle, you could see the flow set points. These are the set points that we ultimately sent to the physical twin. So the permeate flow rate, recirculated brine flow rate here because it was RO with recirculation, and the final brine flow rate. Those are the three flow rate set points you send to the system. And then finally, you could estimate the power consumption of the system. All right. And so what we did here is we said, all right, we want to produce a certain amount of water within a given time horizon. Make sure we do that. At the same time, minimize energy costs. So meet your production targets, but minimize energy costs. And that's why we see this fluctuation in flow rate and power consumption. This was an offline optimization result. We didn't yet hook this up to the live digital twin. So that was our next step. These are results from a WaterTAP driven live experiment with a naive assumption that all of the couple of pumps in the system and the motors, all of that is lumped under a constant efficiency. So even with that naive assumption, here in the middle, you could see the flow set point that the model came up with and sent to the physical twin to be executed. And then on the top, you can see the model predicted power consumption with the orange line. And the black line is the measured power consumption of the physical twin. So you can see there's pretty much like a fixed offset there, which is not unexpected because we use this naive constant efficiency assumption. You can see the mean absolute percentage error is roughly 26%. All right, so we'd like to improve that. How do we do that? We incorporated the pump data sheets for the pumps within the system. We hit a snag with the RO pump, which is mainly doing, consuming most of the power. The manufacturer only had a single curve. So we had to be creative. We used multi-speed curves. We first tried using multi-speed curves from a heavy-duty version of the pump, but then we realized, hey, it looks like they're just using pump affinity laws here. So let's just do that for the single curve and work in the variable efficiency of the pump into the model. So we did that. And they said, oh, let's do the motors too. So we pulled up the motor data sheets, embedded the variable motor efficiency of these two pumps into the system. And after doing that, just a reminder, this is with constant efficiency, the naive assumption. You can see there is, the trend follows well, between the model predicted power and the measured, but there's a fixed offset. And now here is when we work in variable motor and pump efficiency. One thing I will point out is that this run was done after the experiment. So I used the data from the live experiment to drive these results. But what you can see here is that we reduced the mean absolute percentage error from 26 to 4% just by working in those variable performance data sheets. And this is even without doing any power calibration. So we're not even calibrating the model based on the data. This is purely based on the data sheets and the basic equations for pumps. All right. I forgot to mention, you could see the electricity price signal on the bottom, and that's basically what's driving the variable operation of this system. All right. So we had our first WaterTAP digital twin, and we intend to continue working on that. The whole point of that project really for 509 was to inform the full-scale operation of OCWD. Can we have energy savings? How much can we save on energy costs at OCWD? That's something that Diego Rosso and his team have focused on. I don't have any results on that specifically, but I do have another example on a related project where we did just that for Santa Barbara. So working together with Akshay Rao at Stanford University, we basically found these results that you could achieve 18% cost savings. This was done over a particular month. I think it was August. Santa Barbara actually ran the system flexibly and verified that they were able to achieve around 18% cost savings in that given month. So it was validated to some extent, right? So we saw potential here, and we have other NAWI projects that are looking at the same sort of thing. With flexible operation, what benefits can I get out of that? What kind of cost savings can I achieve? But also, what are the repercussions? What are the limitations? What are the bottlenecks of flexibility? So this is an ongoing effort, and we're basically looking to do comparative evaluation across these four systems. So the Charles E. Meyer Seawater RO plant, WRD Albert Robles Center, Chino Desalter Authority, and OCWD. And now I'm going to hand this off to Kirby, who's going to dive into a more detailed analysis, this flexibility approach for WRD. So Kirby, I'll stop sharing and pass the mic to you.
Thank you. All right. Can everybody see it? Can you hear me?
I
Yes?
can hear you. It looks like you have the wrong view.
I have the wrong view shared. Okay, 1 second. Oops. All right, how about that?
There we go.
All right. All right, so yeah, I'm going to talk a little bit about a NAWI project that we did in collaboration with the Water Replenishment District, the Alfred Roble Center at the Water Replenishment District is what we're going to be talking about here. This is a groundwater replenishment facility in southern Los Angeles County. I believe there are some people here from California, so you might be familiar. The source water is a tertiary treated recycled water or wastewater that they bring to the facility to treat before groundwater replenishment. Has a nominal capacity of 14.5 MGD. The target annual production, and this is important, and I'll come back to this, is 10,000 acre-feet per year. So that means they're not constantly running at full capacity. The maximum is about 10,000 acre-feet per year, 16,000 acre-feet per year would be their max. So 62% capacity factor makes it an interesting place to try out some flexibility scenarios. So after they kind of hit this target, they will shut down the facility for about 2 months. All right, so now what are we interested in with WaterTAP with this facility? We put our little WaterTAP pipe on. So in this project, among other things, and what I'll be talking about today, is creating a data-driven model of the WRD facility with WaterTAP. We're trying to estimate the operational cost of chemical use and power consumption, and I'll mostly, actually exclusively, be talking about power consumption in this presentation here today. And then we want to look, once we have our model created, we want to evaluate any cost savings from flexible operations using WaterTAP. So here is the process flow for the WRD facility. WRD has been a fantastic partner, given us tons of data, kind of all the stuff you want: flow rates, pressures, conductivity, time series at the minute level, grab water quality samples, power consumption for many of these units, at the minute level, equipment data sheets, invoices for their electricity costs, chemical costs, the cost of sourcing, the cost of brine disposal, the cost of laboratory, the doses they use, and the chemicals they use throughout the treatment train, even the PV system schematics, and we have some design documents from the water treatment facility itself. So tons of data. From an operational cost perspective, we're kind of looking for like a fixed operational cost as far as this model is concerned: chemicals, sourcing the water from the wastewater, the reclamation facility, and then brine disposal. And then power consumption is, of course, all these pumps for the ultrafiltration, the RO systems, and the UV and decarbonator system at the back end. So I'm going to step through this a little bit. The water comes in through the strainers, which we did not model, but ultrafiltration. There are 4 pumps that bring the water from the equalization basin to the ultrafiltration facility. They have 4 trains, and that's not explicitly in the process flow here, but it is important when you're looking at flexible operations. Specifically, one of these ultrafiltration pumps is redundant, or is a sort of a backup pump, and is not typically on unless they need it to be, so that most are operating with 3 ultrafiltration pumps. All of that water is collected and sent to the primary driver here, which is the RO system. It's a 3-stage RO. We got our data for the PRO, or the primary RO system, and then the TSRO, or tertiary stage RO system. So I'm showing here just the power data we got for the feed and interstage pumps for PRO, and then the tertiary stage RO. Pump power, from there it goes to the post-treatment, which is UV AOP and a decarbonator. So UV typically looks like these are both operating continuously, and then for the decarbonator, typically they are only having about 1. And I'm just using a grab of a single week in August of 2023, I believe, for this presentation here. From there, it is sent to the spreading grounds, and I'm just kind of showing this because I think this is a cool picture and just kind of a cool thing that we do as human beings. But again, contracted for 10,000 acre-feet per year to do groundwater replenishment. The rain can affect this, can cause them to shut down, so they kind of have a little bit of a ability to shut down for rain events built into the facility. Okay, so this is the box that we are drawing around the WaterTAP model that we used, including all of the pumping and post-treatment. And so stacking all of that power consumption for a single kind of typical summer week, this is what that looks like. So on the left is the total power consumption for each unit. We're looking at 3 ultrafiltration pumps and 4 trains. And for the modeling purposes, we kind of assume that these can all be turned on or off or operated kind of independently of one another. And then on the right axis is the cost of electricity based on the time of day. So for this particular pricing structure, the on-peak hours is from 4 to 9 p.m., cost 15 cents per kilowatt, and the demand charge is $39 per kilowatt, 15 cents per kilowatt hour, demand charge of $39 per kilowatt during the peak hours. The mid-peak is on the weekend, slightly lesser electricity costs with no demand charge, and then the off-peak is kind of every other time. So on the plot, the thatched areas there are the on-peak hours, and we'll be looking at a couple of these. So just wanted to point that out. So if we want to look at flexible operations, what we need is a model that's relating the train, the flow and recovery to the power consumption. So we want to be able to modulate the flow rate and the recovery of kind of each RO train, and then get out of that the power consumption. So creating some data-driven surrogate models is kind of the name of the game here. Okay, so how did we do this? Well, I'm going to be talking about some of the stuff that Adam just highlighted as a capability of WaterTAP. First, we took a lot of the data that we got from WRD and estimated the membrane transport parameters with WaterTAP and Pyomo, kind of a built-in tool that comes in the WaterTAP distribution. So on the left, you have the permeability, water, and then salt on the right. All right, we have our membrane parameters. Now we want to develop a variable speed pump model using the nameplate pump curves that we got from WRD. So they were very nice, provided us pictures of the actual pumps they're using in the facility, and also the pump and speed curves for each one of those. So we implemented that in our WaterTAP model, and then we created surrogates for power consumption of all of the pumps for flow and recovery inputs. And kind of the range we used for this came from the WRD operators guidance and from what we saw they were typically doing in the data we received. So these are Pismo surrogates, and this is just kind of showing the deviation from the expected power consumption as a function of feed and recovery rate. So all of that is in our WaterTAP flow sheet. Now we just need to model the post-treatment. We have all the pumps kind of taken care of and calibrated. So we also created surrogates for these 2 units. It was a little bit more straightforward. The UV power, we just kind of looked at the data versus flow and said that looks pretty linear, and used a linear relationship for UV power consumption. And then for the decarbonator, much less power consumption than everything else. And so we just kind of let it as a constant power source or power consumption of about 2.5 kilowatts. All right, so now we have our WaterTAP WRD model. We can put in the flow rate and the RO recovery that we want to get for each train. And out of that, we'll get of course, the water produced, but the power consumption, chemical costs, and brine disposal cost. The chemical costs are largely fixed because the dose is fixed. That's not something that we considered, at least in the analysis that I'm going to present here. But brine disposal costs, as far as like a knob to turn in the optimization, may have come into play. You can see the model may sometimes opt to not create more brine if it costs more. But typically what we're really talking about here is optimizing operations around power consumption and how much electricity costs. So with that model, we have this fantastic data set from WRD. And here's just an example of running that model against the WRD data. You can see the WaterTAP modeled power consumption comes in slightly under the WRD data. And we think that this could be because we're overestimating efficiency of the motor or the VFD, which we did not have super great data for. So we kind of made some assumptions there, or there could be some small parasitic loads that are coming in to the data that we aren't accounting for in the WaterTAP model. But nevertheless, pretty close. And it's certainly useful enough to do some scenario analysis. So what are we talking about? Flexible scenario analysis. We kind of came up with 2 operational modes, 2 flexible modes, if you will. The first is modular shutdown, and this is where we allow the trains to operate at their kind of nominal max flow and recovery, but they can be turned off or on. In the model, we say, and this is based on engaging with the WRD operators, they want to keep at least 2 of the RO trains on. So we say, okay, you can turn all but 2 of the trains off to reduce power consumption during peak times. And they also say, once we turn it, if it gets shut down, it takes about 2 hours for the water that's produced from our RO systems to get on spec. Okay, so that we add that as a constraint in the model. That means for 2 hours, we're getting sort of penalized for operating in an RO train without getting the benefit of the water production. The second mode is sort of like maximum flex. And this would be allowing the trains to have a variable flow rate. And this is coming from the WRD operators. They say this is the typical range that they like to operate each of these pumps in. So we kind of put that as a constraint in the model. We also allow them to have variable recovery. The overall train recovery is going to be between 89 and 93%. It's not a huge range, but it is a little bit of a knob that we can twist when we're trying to optimize the operations around power consumption. We assume that ultrafiltration is fixed at 96% for each system. And we can also look at different electricity rate structures. So not really flexible operation, but like what happens if you use different electricity rate structures. The one that we use kind of as a baseline is the time of use plus prime. I already discussed that. Demand response is the utility says, hey, we have a high demand, can you shut down and we'll give you some money. And then real-time pricing is pretty much exactly what it sounds like, kind of the going rate for electricity in real time. Okay, so coming back to this stacked plot of power consumption for the sort of typical summer week, this is business as usual. As you can see, they're kind of operating constantly. They're not really doing any kind of planned shutdowns to minimize costs during the peak hours. They are turning off some of the components, but not really in coordination with a grid price, maybe maintenance, we're not sure. So in this example, kind of typical week in August of 2023, they produced 289 acre-feet of water. This was the the rate structure that I just discussed. So business as usual, this cost them about 50 grand in electricity cost for this week. Now, why is this? It's because they're operating, most of this cost is being incurred because they're operating during peak hours. So if we put our little WaterTAP pipe on, you can see, try to put this in the optimizer, maybe what you might expect, but it says WaterTAP is essentially saying you should not be operating during these peak hours. Maybe intuitive, maybe not. But again, still producing the same amount of water, using the same rate structure, but with flexible operations, the electricity costs for the week go down to $38,000, and that's about a 24% reduction over business as usual. And so what is WaterTAP telling us to do here? It's essentially saying, during peak hours, turn off one of your ultrafiltration pumps, turn off 2 of your RO trains, and then reduce as much as possible the flow and recovery of all the other components in the treatment train. And then the rest of the time, you're essentially turning everything on, going full blast and producing as much water as possible to hit the target that we set for this case, which would be 289 acre-feet. Okay, so just to kind of touch on some of the other analysis that we did, there isn't really like a typical week. So we kind of contrived this baseline scenario where we said, just like as a point of comparison for other rate structures and flexibility scenarios. So we said, okay, let's say that they're operating with 3 trains on, operating at kind of nominal capacity the whole time. So we have 3 trains operating continuously. We're saying that the target production per week is 230 acre-feet. And then this costs $35,400 based on our modeling endeavor. We like this as a baseline scenario because, again, you kind of have this 30% or so capacity that you can use to flex your operations. And so from a power consumption standpoint, constant operation, like I just mentioned, $35,000 in electricity costs. And so this is just a point of comparison for other operational scenarios. So what do those other different scenarios tell us how much money we could save? So for example, modular shutdown revealed 8% savings over the baseline week. If you do the maximum flex with kind of the baseline rate structure, you can get up to 16% savings, similar to what Adam showed earlier for the Santa Barbara facility. If you combine modular shutdown with a demand response, there's a really high amount of savings, but there's an asterisk there because some of that is revenue that's coming to you for the demand response event. And that profile is on the left here on the slide. And just as another aside, you can only do that 60 hours per season. So maybe you wouldn't be able to realize those savings constantly. And then finally, kind of maximum flex with real-time pricing, you can only see about 7% savings. So just kind of an example of the type of flexible analysis we've been doing for WRD. So just to quickly wrap this up, using WaterTAP to create these data-driven models, creating surrogates, is super useful for evaluating different operating schemes. Like we just showed, you can provide some significant energy cost savings by flexibly operating. WRD may be kind of like the best exemplar for flexible operations. First, like I said, they have a higher capacity than they need. They kind of have a little bit of room for flexibility. They can produce water whenever they want. They just know they need to produce 10,000 acre-feet per year, can kind of do it whenever it's cheapest. That enables more flexibility. It really helps that the primary kind of treatment technology they're using is membrane-based. These can be a little bit more flexible than maybe other conventional water treatment technologies. And just the WRD operators and people that we've been engaging with are extremely motivated to save money and kind of maximize their savings because they know that they are kind of this unique, they have kind of a unique situation. And of course, they were very, 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 very nice to provide lots and lots and lots of data. There's plenty of spreadsheets that they provided to us that I have not looked at, but it is extremely useful and makes this modeling exercise much easier. So finally, I'll also say WRD is actually experimenting with shutting down in August rather than May. So right now, their kind of water year ends in July. And so they like to produce as much as possible up until they kind of hit their 10,000 acre-feet. And that has been around May in the past. So they're producing water during the most expensive time of the year in the summer. And so they're looking at shutting down in August. And as part of this partnership with them, we've been able to provide data and analysis to them to bolster and validate that decision. So that's been pretty exciting to come out of this collaboration. And finally, I'll just say, of course, I did not do all of this. There are two fantastic colleagues at the National Laboratory of the Rockies who have also contributed to this significantly. So yeah, that's kind of all that I had. And I guess I'll hand it over to Elmira.
Thank you, Kirby. I'm going to share my screen. Can everyone see? Can everyone see my screen?
Now we can, yes.
Yep.
Okay, perfect. Okay, so I'm going to cover the industry collaboration that we did with our amazing partners at EPRI and Tech. I see Jason and Muhammad are in the audience. Thank you for joining, Jason and Muhammad. So I start this industry collaboration with the question that we were trying actually to answer. That when you, and many treatment engineers, water treatment engineers are familiar with that. When you have a treatment train with different process unit in it, and you have chemical and chemistry on the other side, what tools you are going to use to integrate these two together to design and optimize your system? So before going to the method that we use to answer this question, I will quickly recap the case that we studied on. It was a mine contact water from Tech side with 3,400 milligram per liter TDS. It was sulfate dominated and characteristic of mine contact water, and with calcium and magnesium hardness. That was the problem. And it's being treated to discharge target, and there's a residual brine that needs to be managed today, and that's the main problem actually that we are going to address. And so the objective of this collaboration was to build an integrated model of chemistry and both process modeling, coupling these two together, that the existing tools cannot capture that. So I start with the process treatment train that we are going to model. The water that is going to be treated is a mine contact water, and the process is established. It starts with some pre-treatment acidification and goes to some reverse osmosis filtration, and it meets discharge target. But the main problem is the bleed stream that is left. And that is going to determine the cost based on the volume that is left over, and it needs to be minimized. So, and the solution to minimize that final brine is probably the obvious answer is that to increase the recovery in this process. So, but how do you really increase the recovery so that you don't have this scaling problem on your membrane? You increase your recovery and you will get gypsum and calcite scaling on the membrane, that's exactly the place that you don't want that. So there are two knobs that industry uses. First, direct one, increase the single pass RO recovery. The other one is add this recycle loop and pass that brine that is coming out of the reverse osmosis passes through some softening step called high density sludge or HDS, and then again recycle that back to your system so that your overall recovery of your system is high, but your reverse osmosis step is not pushed to its highest extent to the scale. But this, again, is not easy and it's not straightforward to do so. You need to have real and accurate calculation, rigorous calculation of your scaling when you are also doing the modeling and design of your whole treatment system and this whole flow sheet. And also, right now, when you add this recycle loop, whatever you change within the design of this softening reactor will change the input to your RO, and it affects your RO design, reverse osmosis design. And changing your reverse osmosis design directly affect what you are saying in your softening. And this is not easy to close this loop in just manually or manual iteration. Now, what industry is using now to address this problem? They're using different tools, fragmented. I will start with showing them. They do, for example, start with some feed ion balance in Excel sheet, and they do some acid addition to reduce the pH. And then they do some reverse osmosis analysis in software such as Wave, and there are other software as well. And they control the LSI for calcite there again. And then they do some constraint check for the anti-scaling dosing with some other softwares like Avista. And then again, they do use for their softening step, they use some chemistry engines such as OLI. And then they use, because none of this is connected together, they do all the calculation for supersaturation and clarifier and reagent dosing and everything. Again, they do the manual chemistry calculation in the Excel file. And again, they do, after they have done all these steps, you have the recycle stream that it should go back to the first step, and they have to repeat this step again and again to converge. So this is, as many of you already know, this is miserable to do all these steps together and together to converge to a point, and this is not a system that gives you actually an optimum result. So, but the good news is that with the work that we are doing in WaterTAP, those dark days are over, and I'm about to show you how we're going to address that. So the way we are integrating these, we are going to integrate chemistry with our process model is that we are integrating a chemistry engine we are using here for this example case study reactor open source. We are coupling that with WaterTAP. And for WaterTAP, in WaterTAP flowsheet, we do have a stoichiometric reactor. We do have multi-component unit models. We do have property costing models and property and costing models. And it solves all your unit model processes at the same time together. And we integrate that, we couple that with our thermodynamic engine, which is reactor, which comes with speciation, equilibrium chemistry, pH and alkalinity tracking, saturation indices, and automatic feed reconciliation. We integrate these two, we solve these two simultaneously together. And we also calibrate all these models, these two models coupled together with the very valuable feedback that we received from an industry partner from Abraham Tech Resources. So the feedback we received was one of the most important ones was regarding the gypsum supersaturation targeting, for example, that no matter how long for longer hours it sits in the reactor of the softening, but you still have supersaturation of gypsum, that we include that modeling in our consideration. And you have different slack line reaction efficiency, and you need to consider which ion to use for the feed reconciliation. After coupling all of this together, you will have your lab chemistry in, your measured alkalinity in, and something that was once in previous slides, some fragmented measuring and calculation, now it becomes automated and everything solves together simultaneously. You will have integrated process chemistry, you will have automated solid and reagent calculations, you can do design space exploration, and you can, most importantly, you can do system optimization as a result of this design space exploration. So I'm going to show you now when we run this, we will get a lot of insightful results from chemistry of each step of this process and also the overall system design. And what I'm about to show is just because we don't have time, a few examples of the results. I will start with the chemistry. And this chemistry that I'm going to show you is not as a result of solving just the softening steps. It's solving the full flow sheet from reverse osmosis to softening to the recycle to the mixer to the acidification. And I'm zooming in on the softening flow sheet chemistry, softening step of that flow sheet chemistry to show you. So starting with this graph, it shows, for example, how much precipitation of our main solids that are calcite, brucite, gypsum that we have, and how they change if we change the operating pH of our softening. And starting with calcite and the blue one, you will see that it's in a normal pH range. This is the dominant precipitant, and it starts to plateau after pH around 9.5. And the beauty of this work that we are doing at WaterTAP is that you can see the underlying reason in other results like that. For example, you want to know why calcite is behaving like this, you will have the alkalinity graph result as well. And this shows you why. It shows you that the alkalinity in and alkalinity out of to your softening reactor, they are converging together as you're increasing your pH. And so it shows you that your calcite precipitation is actually alkalinity limited, and that's why you will see that it's this plateauing trend for your calcite. So, and let us go to brucite. After raising pH over 10, you will see that the brucite start to appear, and that is in conjunction with increase in our slack line dose sharply after increasing the pH over 10. So, and one might ask, why should I operate my plant in this region at all when I can have my magnesium if its level is not that high that cause problem? But the answer is that you have that recycle loop that goes back to your RO. And that recycle loop is going to accumulate your magnesium pass after pass. So, and the only place that you can take out this magnesium is with your brucite at your softening step. So that's why you will see you have to operate your plant at pH over 10.5. And the reason that you're seeing this sharp jump on the slack line dose is that brucite uses double hydroxide when it wants to precipitate, and also for every unit pH increase, you need 10 unit hydroxide, which is logarithmic correlation. So the beauty of this work is that, again, what you see, you can see the underlying reason behind that as well when running with WaterTAP integrated with chemistry and drawing. So let's go to gypsum. You will see some constant trend for gypsum here, and that's on purpose. That was based on industry feedback that gypsum will be maintained at certain supersaturation level in the softening reactor. But why it start to form more gypsum as soon as we start to have more brucite? Again, you can see the results in other result of the underlying reason on other graph of the result that shows the ion removal efficiency. When this brucite is going to form, it leaves behind this sulfate. And this sulfate is now going to precipitate with gypsum. That's why we are seeing the gypsum is forming, that the reason is this sulfate that is being precipitated after magnesium precipitation. So this might seem complex, but my main goal is that by doing this integration and coupling analysis, you can zoom in every part of your process and see the exact chemistry and what's happening behind that, so that you have quantified every decision that you're going to make. So I'm going now to shift toward the system level analysis, so that we see that that's what about the goal that we had, increase the recovery while we are meeting the scaling targets. So let's zoom out and let's see what happens within our process flow sheet with that recycle loop, and what happens to our scaling on the membrane surface. What you're seeing here is the scaling tendency, which is defined as ion activity product by the solubility product. And a scaling tendency equal to 1, meaning you're at equilibrium. More than 1 is supersaturated, and under 1 is undersaturated. So, and what you see here is the scaling tendency at the outlet of your reverse osmosis membrane, meaning that it's most concentrated state. And on the y-axis, you will see reverse osmosis single pass recovery, and on the x-axis, on the y-axis, you will see overall system recovery. That is an indication of your recycled loop volume. So, and what you see here is that calcite scaling rises more strongly with the reverse osmosis recovery. And as you increase the overall system recovery, the recycled feed chemistry becomes diluted in a way that it reduces calcite supersaturation. We will see some kind of same trend for the gypsum, but for the gypsum, it's more correlated with the reverse osmosis recovery, and the reason is and not the overall system recovery, and the reason is the same supersaturation state of gypsum because of anti-scale and dosing that I mentioned. And you can also see how your slack line dose changes based on the change in your reverse osmosis recovery and overall recovery. But the question is, how do you decide which one of these points you choose to run your system? Now that you have all those chemistry inside, and you have this scaling inside and your RO plan, and you know that what is the volume of your recycle loop. So the answer is, so we have seen scaling risk and line dose rise with RO single pass recovery. But the question, but is that the answer that, okay, reduce RO single pass recovery and increase the recycle loop volume? No. Lowering the RO recovery forces a larger recycle loop, meaning that the volume of that recycle loop increases. And increasing that volume will increase the size of mixer, softener, clarifier, pump, everything in the upstream of that unit. And we have seen in our analysis that, for example, reducing the reverse osmosis recovery from 80% to 60% grows the system size to 30%. So the answer is in the next slide. What we are going to do based on the industry feedback is that operate your system on a point, push your RO recovery to the point that it's before that binding precipitate scaling constraint. And here our scaling constraint is for gypsum. We analyze everything. We analyze the whole flow sheet in regards to calcite, and we saw that we are at any operating point, we are under the calcite limit of LSI 1.8 that industry partner gave us. So we were left with the scaling constraint for gypsum, and we saw, and the goal was, and based on industry guidance, was push your RO recovery as high as possible so that you are meeting the scaling constraint for the gypsum. And here on the left graph, you will see that. We have RO recovery, we have gypsum supersaturation, and we will see that saturation ratio, and you will see that at this point we have the sweet spot, meaning that we are at the RO recovery of 73%, and we are still meeting gypsum supersaturation of 4.5, which was an input from industry to us in their pilot. They have tested that. They could go up to a high 5 or 6 supersaturation for gypsum to minimize the size of their plant, but we stayed at the cap of 4.5 to be on the safe side and the resilient side of the gypsum scaling control. So, and this way, when you operate at this level, push your RO recovery, you can by keeping the overall system recovery at 95%, you will see that you can reduce your recycle flow rate significantly, and you can reduce that. This means that you can reduce your system size significantly. So this is all the beauty of this analysis, that you can, from chemistry to system size to exactly quantifying sweet spot of your operation. We have so many other results regarding the pump pressure, how it changes that, how you are going to, and also we have some preliminary T analysis that we are going to complete. But I'm going to close the result analysis here and just show you that this is, for example, a proof of full flow sheet solve with our solver, that it gives you all the stream characteristic for any stream for each of the units within that flow sheet that you have. And you can see that you could solve that for 95% recovery, and you could have a very concentrated brine leaving your system. And to wrap it up, this kind of integration from chemistry engine with WaterTAP, it was very promising case study that we did. We could solve that for full flow sheet solve. We could obtain sweet spot for 95% recovery at 73% reverse osmosis, while meeting the cap that industry gave us for the scaling indices. And also, industry showed us again, they could go up to 6, but we capped that at 4.5, that we are going to analyze that with other scaling cap in our further analysis. And for future, we are going to validate this against the full scale plant data. And we are going to include, to have more detailed treatment train plans. For example, we are going to include ultrafiltration there, and we are going to have more detailed T analysis there. And we are also going to continue refine the WaterTAP unit models and we want to make it as much close to real plant operation data as possible. So thank you all, and I pass it to Adam.
All right, thanks for sticking around, everybody. Amir, if you could stop sharing, I'll just finish off with the last slide or two. But yeah, I know we're over time. We packed a lot of information in today's presentation. Just waiting for the stop share.
We didn't go over time. This was all bonus content, friends, bonus content. And this is, of course, immortalized on NAWI's YouTube site. So I imagine a lot of you are going to be listening to this in the future. Fabulous work, you guys. Adam, take us away.
I just want to finish up with our simplified conclusion that WaterTAP's main objectives are to provide value to pilot projects and industry stakeholders through case studies to help solve challenging problems. I hope you caught a glimpse of that today, right? We walked through a couple examples on pilot projects that we've supported, and a couple of examples of industrial case studies that we supported, whether it be flexible operation or pushing the limits on high recovery RO for mine contact water and accounting for detailed chemistry. On top of that, I also just want to remind everyone that we have our second cohort of the WaterTAP Academy planned for this year. The exact timing of that is a bit up in the air, but we're hoping for this fall, so keep an ear open for that.
If you are interested, reach out to Adam or the WaterTAP contact here and just let him know to keep you on the list.
Yep. Once again, call to action, reach out. We're here to support, provide technical support with WaterTAP. We have a great team shown in this slide and this slide. And we have a lot of people to thank, but no time to thank them. So I just have their names here. Thank you, everybody who's ever helped any of this work. And yes, here's our contact information. So for general inquiries, you could reach out to watertap-contact@lbl.gov. For technical support, watertap-support. Here's our main repository, our documentation. And if you want to reach out personally or directly to me, here's my email. All right.
Great.
Thank you, everybody. Thank you, Kirby and Elmira, for the great presentations. And thank you, Peter, for giving us the
You
venue.
guys, thank you so much. And it was important that
you.
we run long because of such the value and the depth of what you guys have done. I want to still say that we have time for questions. If anybody wants to write a question into the chat, I will say, just kind of repeat what I said in the chat earlier. I guarantee you in 5 years' time, new advanced water treatment plants will have advanced modeling, not only at the outset of the design process, but the capital planning and budgeting process will have this level of design. You can, Kirby, your work alone showed the gargantuan cost savings, the truly important cost savings that can come simply from doing this work up front. And Elmira, your work with just one company shows how much more performance and value can be obtained from integrating those questions into the outset of designing an advanced water treatment system. I could have predicted this question, Catherine. Thank you so much for asking this question. Has a graphical user interface been released yet? Adam, I'm going to throw that to you, but I'm also going to invite you to explain a little bit about the complexity and kind of what is necessary for a graphical user interface to be a success for users.
Sure. So the answer is yes. We've had a graphical user interface for some time. It limits the full potential of WaterTap. So you'll be constrained to whatever flow sheets have been made available in the UI. What it can't do right now is you can't flexibly connect units together as you please. What you can do, though, is take prescribed flow sheets, run simulation and optimization on those flow sheets.
Yeah.
All right. And that's where we stand. It does take quite a bit more effort to make things more flexible in the GUI, where a lot of people want the drag and drop capability. It's not quite there. And I'll also mention we're actually not funded by the DOE to do that. However, we are open to working with collaborators if people are interested in delving into that with us. We have the capability, just not the resources.
That's right. And if anybody on any aligned DOE or Bureau project or program wants more capability, come and get it. But it needs, it takes a village. Adam, I'm also going to throw another question out to you. Obviously, with the rise of large language models and the ability to now have AI shape the interaction between kind of an advanced platform like this and a quote unquote more novice user. Where do you see this going? And do you see there potentially being a way in which, what still does a user need to hold in their hand as opposed to having an AI intermediate some of the either the coding or the assembly of some of these models?
So I would say using Gen AI, you could probably get a nice jump start. If you don't know how to code or anything like that, you know nothing about WaterTap, you might get a couple of nice scripts spun up for you that might look like they do something. What do people need to hold in their hands? Probably the hand of a WaterTap developer.
Clutching.
Hold on tight so that we can tell you whether AI is giving you hallucinations or not. And from what I've seen, people have come to us a couple of times now. Hey, ChatGPT gave me this code. Can you just check it for me, see if it's running? And they put together this masterpiece of a flow sheet. I'm like, oh my God, this maybe you should lead WaterTap. But then when you run it, you see that it's not functional. It's just you have to go under the hood and fix things up. So I would say it's a good jump starter. It'll definitely help with debugging. If you are a developer, it's streamline and reduce the time it takes to develop models. Once we get broad approval to use these tools across the board. So there's a lot of potential, but if you're a new user, be careful.
And I would also say, look, ultimately having, I want to say an instinct, but some familiarity with process modeling and process, the concepts of process simulation, process modeling, very important. The other thing is, I know that like a typical consulting engineering firm, most of the consultants are not like Python people. And that was the number one thing that I heard. My version of that same complaint was, oh, do I need to learn Python to use this? And the answer is we're journeying together, right? To see how hands-on or et cetera. And I would say that that's probably one of the most exciting possibilities I see in the next 24 months is watching how we have a new cohort of users come into the second class of the NAWI WaterTAP Academy, and maybe together begin to test out some of these interacting tools between an AI assistant and the sort of coding that one's still going to need to do in assembling and testing your models. I don't see any other comments or questions here. We have gone long, but it has been delightful and juicy. So you guys, fantastic work. And honestly, from all of us at NAWI, we so appreciate the frontier that you all continue to push forward in advanced process modeling. And these stories you're telling and the ways in which you're showing us the results, it's truly exciting. So from all of us at NAWI, thank you. Thank you, everybody in the audience today. And please stay in touch as we stand up the second academy. And please reach out to Adam and the team with any questions you have. From all of us at NAWI, thank you very much. And we'll see you next month. Bye-bye, everybody.